technical fleet manager at Allegiant. I am primarily involved with keeping the airplanes in the air. I do a lot of troubleshooting. Mostly, my strength is avionics. Do a lot of engine stuff too, but I was originally supposed to be an electrical engineer as a career, and I got tricked into aviation, and here I am. So nice. I do have a lot of electrical background. That's primarily what I do with the Airbus, because it's an electric airplane pretty much. So first off, when people say electricity, you flick a switch and something happens. I mean, you can't see electricity in the sense that with your naked eye, but you have these things called electrons. Electrons are what create the light to come on, the motor to move, everything. They're everywhere, and electrons they're just sitting everywhere. They're sitting in the atmosphere. They're sitting, just waiting for something to do something or something to move them, and that's what electricity is. We will take. I'll start off with the simplest form is a battery. Everybody knows what a battery is. A battery is a container that holds electrons, just sitting in there waiting for something to make it do something. So I'll draw this little here.
Just hold it like a regular pen, baby. Yeah.
I'm working. I just don't want to put my arm on it. I don't, because if I touch it, is it going to make a? All right. I don't want to hit anything on this and not do it.
It's fine.
So you have a battery. It's filled with all these little electrons. Electrons are, you kind of get the point. They're just little balls of energy just waiting to be done, waiting to be moved. So every battery has two sides, a positive side and a negative side. Looking at that, in a current state battery state, nothing is going on. You have your little, I guess I can draw a 9-volt. You have a little, two little tabs at the top, and the what's the word I want to look for? The tendency for electricity is, this is where I'll get the flat earth thing. Electricity flows negative to positive. I can't draw up there. So
it's a little dented on.
Oh, is it dented?
Pen thing.
Oh, okay. So negative to positive is what it wants to do. It tendency wants to do that. You have the people that are the flat earthers believe that it goes from positive to negative. Where's my that's a race? Because I just did the race thing. So if you think about it, so we have a positive charge here, negative charge here. Negative charges are called grounds. All right. So you're going to hear that consistently through electricity is a ground. It's short to ground, something to ground. The reason because it goes back to Ben Franklin and the kite. So you had the kite up here, you had your little cloud with a little lightning bolt, and you had your little kite here with the string and a little Ben Franklin, and lightning struck, and it went to the ground. So that's where that comes from, the ground. So people believe that lightning, is looking for the ground. So electricity is looking for a ground. So that's where you'll have that phrase short to ground. So so that's that. That's just a little brief little, horrible animation of, Ben Franklin is when we say ground.
I can see where Maggie gets her drawings from.
Yeah. It's I'm a horrible drawer. That's what I don't do. But those are the people that, at this day, those people are considered flat earthers because the electricity doesn't go to ground. People believe that electricity leaves ground and goes to the positive. So that is what I follow. I'm not. There's people out there that will try to rebuke me to this day, or dispute me.
Wait, are you a flat?
Okay.
No.
No. Electricity travels negative, or it travels positive, negative positive, but it's
negative to positive.
Yeah. That is the way. Every time you look at an electrical schematic, you start at the negative and you go to the positive. There's people that start at the positive, go to the negative, and it's opposite of what I'm going to say. 99% of the people in the world go electricity travels negative to positive. So I'll just leave that at that. But so you understand that electricity, it's looking for a path. It always wants to move. It's sitting here like this is not what it wants to do. So you have to create something called a circuit. A circuit will cause electricity to move. Let me see if I can get eraser going here. Pixel eraser, I guess. Okay. All right. So we're going to take our battery here, and we're going to create a circuit, a simple circuit. So we're going to have, say, a light bulb. So I know it's going to be a horrible drawing.
That's cute.
I don't know. So here's your light bulb, your little filament in here. And then along with the light bulb, I'm going to put a switch in there. So say this is a cockpit switch. This is how we draw a switch in electronics. It's just a little lever that, it'll go up and down.
Yeah. Gorgeous.
So there's our little switch. So what we need to do is we need to have a complete path for this. So we have a wire that comes out and goes to the one side of the switch, and we have the wire connecting to the light bulb and the wire going back to the battery. So this is a simple circuit, and we have our switch here. What?
Oh, the cat just.
Oh, yeah. Cat just dropped the bomb in the house here. Yeah. Maggie's grossed out. Okay. Anyway, so sitting here, there is nothing going on. No electricity flowing. Just you have the battery, the switch, and the light bulb with some wires. If I take this switch and I close this switch, then I have created a circuit. As long as there is a complete circuit, you're going to have these electrons flowing. Negative electrons are flowing to this light bulb and are going to cause it to light up. And then they're actually, once the light bulb is depleted, you're going to have the same electrons, but they're going to have no capacity to them. I guess what you would say. Once their energy is used up, they actually go back to the positive side.
Okay.
So you actually have, so as long as you have a complete circuit here, you're going to have a light bulb illuminate. As soon as I open this circuit, the light bulb stops. So there's only so many electrons inside this battery before it dies. So that's
Gotcha.
kind of, yep. So very simple, battery switch circuitry. So just all you need to know is there's electrons inside the battery. When you create a circuit, the electrons will move through the wire into the light bulb, light the bulb, and then the empty electrons will move back to the battery.
Okay.
Electrons are neither created nor destroyed. They're either charged or discharged.
Okay. So once the light bulb uses them, then it's discharged electrons are inside the battery.
They go right back into the battery. Correct. So that's why when you start seeing a light bulb get dim, when a flashlight is pretty much you're running out of electrons and everything is dying up. Now you can have a rechargeable battery where you can recharge them and it'll actually reverse the charge inside the battery, but I'm not going to go into that. You need to worry about that now.
Okay.
So that's something that's So just so you know, you have a circuit, you have electrons flow through the wire, through the switch, into the light bulb. The electrons light it up, and then the electrons that are depleted return to the battery.
Gotcha.
So I'm trying to think how I want to. So the electrons can be used to do a lot of things. They do batteries, they do motors. They run your circuitry inside your phone. Everything has any sort of I don't want to say light to it, but if it does any kind of work, and that is what it was explained to me years ago is. The electrons do the work. So, so even, like people will say, does the inside cell phones, they're electrons. It's like, of course. I mean, electrons are switching, little transistors that do all that stuff in your phone that you don't, there's millions of little transistors inside your little phone that do the work. And the electrons are moving in there and they plug your phone in and it recharges those electrons, the same electrons. The electrons never leave your phone. They're always in there. So they're just bouncing back and forth between charge and discharge doing the work.
Okay.
So that is a simple circuit for electricity. And
Cool.
it's a horrible drawing. It's a horrible drawing. I'm looking at it and I'm just like,
Yeah,
oh, it's
I like it.
Yeah.
Okay, so one quick question. So when it's flowing, you have the negative side of the battery and the positive side of the battery.
Mhm.
What's the difference between those two, between a negative and the positive?
Okay, so it's pretty much what you call the potential.
Okay.
The potential is so physically or electrically, are you asking? Like what is the difference?
I think the answer is yes.
Well, yeah, so both.
Yeah,
So
I was gonna say both.
physically there's little pieces of film, like plastic film, in between the battery that separate the positive and the negative side. Electrically, these electrons are sitting there pretty much the way you have to think of it. If you get down, I don't want to get way too into the atoms and the molecules, but you have it's just I don't want to get away. I'm really afraid to get into it.
Do they combine to make power, or
say again?
Or do they combine to make power, or on this side, if it's going from the negative to the positive?
They do not combine to make power. They just move. They just, as soon as you create a circuit, they just start moving through the wire.
Okay.
Yeah, they do not combine at all.
They want to hang out. They want to be together.
Yeah.
Right.
They attract, and that
but
goes.
They can't be together if there's not a circuit to connect them.
Correct. Yeah.
Oh, so once the circuit is connected, is it combining negative and positive through the lines?
No, they're not. The negative positives will never combine.
Okay.
They are just they want to be attracted to each other, but that running through the wire makes them increase the attraction, but they never touch each other.
Okay, they never touch each other, but they're both in the wire at the same time.
Yes, you have to think of it. It's very interesting. It's very interesting how the bonding of like the chemistry of it, I guess is what I want to say, is how it works.
Yeah.
Is they will never positive and negatives will never touch each other.
Okay.
But they will be close. Let's just go that route.
Okay.
But they can never combine to create something new. It's like oil and water. You have oil and water in this line. They're never going to come together and emulsify, but they're in there together.
Okay. So what's happening? I have a question. So what happens when you do the thing where you lick a battery or whatever, and you put your tongue on it?
Your tongue is the wire.
Okay. And that's what's making that circuit.
Your tongue becomes the wire, and what you're feeling is the electrons flow out of the negative side through your tongue, and they're actually in the work, I guess, would be it's creating heat, and it's actually making the receptors on your tongue move. That's what you feel, that little tingling feeling.
You should try that, Cooper.
Have you ever done that? Stick your tongue on a 9-volt battery?
I'll neither confirm nor deny, but I am a guy.
Yeah. I mean, most people have done that. But that's what you're feeling. Your tongue is the wire, and you're feeling the electrons move on
just making sure it's still a good battery.
Yeah. So
but absolutely, I'm doing my duty, my service.
Right. So yes, just for your sake, all you need to know is you have electrons. The electrons do the work. They move through the wire. They make the light. They make the motor move. And they go, you have positive and negative charges, and they go back through, back into the battery. It's all you got to know.
Okay.
Again, I could get into the chemistry with covalent bonding, K and P and N,
no doubt about that.
Shells, and you don't want to. Even for me, it's chemistry. It's not even electricity at that point.
Yeah.
It was so. So that I'll leave. So leave it at that. Just say, the electrons will never combine. They're always going to be positives or negatives.
Okay.
And just that's how we go. So you'll notice in the airplane. I'll throw this in here right now. You have the wiring inside the airplane. Have you seen areas like in the aircraft be shown with wires and everything?
You can look up under the dash and see some wires.
So the thing about airplanes is that the airframe is metal. because the airframe is metal, it is a good conductor of electricity. So what they figured out a long time ago is I don't need to run 2 wires to run a light bulb. I only need to run 1 wire to operate this light bulb. I don't know if I can release this. It's easy as that. No, sure. Is there a bigger way to make it bigger or no? No, I guess I gotta do it this way.
That's fine.
So instead of running 2 wires to run 1 light bulb, they figured out that, hey, everything on this airplane goes back to ground, and ground on an airplane is a common point. So every electronic component on that airplane will go back to that battery up in the cowling, right? So what they have figured out is they have taken a wire off the battery and they have attached it to the airframe. That's horrible. And they have taken a wire for the light bulb. They've attached it to the airframe. I just put an A there. So in reality, the airframe now becomes a wire.
Okay.
So you no longer need 2 wires. All I need is or 2 long wires. You need 1 wire going to the light bulb. Then you need a tiny wire going from the light bulb and touching the metal of the airplane. Then you need a 1 wire going from the battery touching the metal to the airplane. And the electrons will actually flow through the airframe, under your feet, above your head. They're flowing through the airplane. So
nice.
They have eliminated half the wiring needed on the airplane just by using the airplane metal frame as a wire.
Okay. Cool.
So yeah, and this is only true for metal airplanes. If you have composite airplanes, you got to run 2 wires because
Cirrus.
Yeah, the Cirrus will not is not a metal airframe, so you have to. In theory, it's a great airplane, but they've had to double the amount of wiring on the airplane just because the airframe is not metal. So yeah, so it's like have you ever opened the hood on your car and you seen the terminal for your battery? Have you ever looked at those?
Yeah.
Mm-hmm. Your car is the exact same way. Your negative terminal of your battery goes and just attaches to the frame of your car. It's just a giant bolt that attaches anywhere to metal, and everything else in your car attaches to another piece of metal somewhere in the car, and the electrons will always find their way back to that the battery. It'll go through the frame of your car. Okay. So it's kind of way they figured out weight savings. It's like, why am I doubling the number of wires in an airplane when I can just use the frame of the car or the frame of the airplane? It works. So
yeah. Okay.
Kind of on a grounding note, can you tell me why when they come to fuel the airplane, why they connect the truck to the aircraft?
Oh yeah.
They take a
for me?
Yes,
I thought I meant for him. Okay. I'm sorry.
No,
I was like, I have no idea.
So it's pretty much static electricity. This is the number one reason why you attach the airplane to the truck, and you're actually supposed to attach all 3 or both the airplane and the truck to a point in the earth on the ground. A lot of airports have grounding terminals in the concrete. It's just a giant metal rod that goes about 20 feet down into the ground, and it goes back to the Ben Franklin thing where lightning strikes. You want it goes to the ground, and when lightning goes to the ground, it dissipates. Well, the same thing with electricity. If you have static electricity, you want it to dissipate. You do not want any sparks around fueling, of course.
Right.
A lot of people don't realize they see that spark. When you're a kid, you rub your socks on the carpet and you touch something metal and you saw that spark, right?
Yeah.
A lot of people don't realize that's a couple thousand volts jumping from your finger to that metal.
Wow.
Yeah, it's like it's small. So I don't want to know when to segue into this. So
we can mention it and then we'll come back to it.
So I'll mention now. Voltage does not kill you when you get electrocuted. It's current that kills you. Voltage is just the enabler for these electrons to flow. It is not it is not what does the work. It's pretty much, yeah. It doesn't. I guess voltage is. I don't want to explain it now if I just want to get into it later. I'm just sorry.
We'll put a pin in that and we'll finish the conversation about that.
So the grounding of the airplane to the truck is that you want them to be the same potential. Same thing with your socks and the piece of metal. The reason the spark jumped from your finger to the metal is because you had a difference in potential. By attaching the fuel truck to the airplane, you make them the same potential, so there's no chance for a spark to jump between the truck and the airplane. And that little spark can ignite the fumes of the fuel and cause an explosion.
Okay.
So,
Cooper, when you get out of your car, like in the wintertime, have you ever gotten out of your car and shocked yourself on your car door?
Yeah.
If you hold that car door and then scoot your butt out and then keep your hand on the car door before you stand up, you won't shock yourself because you're keeping yourself grounded while you scoot.
Oh, okay.
Yeah. So it's all about potential.
Yeah. So while you're sitting in the car, reach out, grab the metal of the car door, and then get out, and you won't shock yourself.
Okay.
Yeah. So think about the way of a battery. Your car door is the positive of the battery. You are the negative. When you touch that car door, you become the wire, and it flows through you.
Oh, okay, gotcha.
So
yeah.
So that's how that way. And the same thing with the airplane and fuel truck. You want them to be the same potential because there's no chance for current to flow.
And that's why we're getting into, how we have the static wicks on the airframe, right?
Mm-hmm.
Those little doodads that kind of stick off there.
Yeah, off the back. Yeah.
When the airplane's flying through the air, it's building up static electricity from the friction with the air.
Okay.
And so the airplane
that's why they have
actually, that dissipates the static electricity. Otherwise, we could get damage to our avionics, to our radios, could get crackly radios, that sort of thing, just from the buildup of static electricity on the metal airplane.
Okay. Gotcha.
So that's why we have those static wicks.
Okay. Nice.
Talk about volts and amps now.
All right, volts and amps. All right, how do I clear this up completely?
You can
Just
do here. We can just make a new. We'll just make a new one. Here you go.
All right, just that's it.
Yeah. Yep. Oh, hang on. Let's the drawing thing.
Okay.
And then you pick down there. Yep. So you got all different colors.
All right. So everything in electricity has three parameters. You have voltage, you have current. I'm not an Apple person, so I don't write on iPads. And then and then you have resistance.
Okay.
All right. So voltage, we call it V, volts, right?
Mm-hmm.
Current, we normally don't, in everyday life, we don't call it current, we call it amperage. Okay. So you've heard of, your battery has an amperage, your vacuum cleaner has amps. Everything has amps.
How many amps does our electrical system have, Cooper?
Our
alternator puts out how many amps?
Was it 16?
60.
Let's see. 60. Okay.
60. Yeah. I'm sure that's what you said. I'm sure I just misheard you.
Yeah.
Yeah, sorry, it's just Wi-Fi's bad here.
Yeah.
I know it's 28 volts.
Yeah, it's an alternator puts out 28 volts.
Yeah.
So you're gonna see your voltage. We refer to as V. Your current is A for amp. And then resistance is R.
Okay.
There's a guy out there years ago, way before one of us. His name was Ohm, and he created a law, and it's used to this day for everything. And pretty much, you're able to calculate your current, your voltage, your resistance with a simple formula. It's very simple. You're never gonna have to do it, but Just so you know, it's out there. So they have taken everything that electricity is designed off of this simple formula. So on your airplane, you have your. I don't even want to draw an airplane. I'm just going to draw a battery. So you have your battery. Yeah. So you have a battery, has a positive terminal and a negative terminal. And let's say you have your. I want to do this. I'm going to say your alternator here. Let's do that. Alt. Okay. And then we have your, I guess your airplane systems. All these three work in tandem. Do you know what the alternator essentially does? Real simple.
Charges the battery.
It charges the battery. It takes those used electrons and makes them usable again. Is pretty much what we do. So alternator will actually tie. I'll say I want to draw it as good as I can. It's in it's right. It's electrically it's in parallel with the battery. It works hand in hand with the battery to not only charge the battery but actually operate your systems on your aircraft. So
okay.
In reality, we have it's daisy chain. It goes to here and it goes to here, goes to here, then goes to here. Do you know what happens if your battery fails while you're flying?
We lose power.
Right. So do you lose all the power, or does it give you a do you have a standby battery?
We have a standby battery.
Standby battery, yep. So on your car, so I guess so when your battery dies in your airplane, does the engine fail?
No.
When you're driving your car and your battery dies, what do you think happens?
Your engine fails.
Engine fails, yes. So it goes back to this whole thing where you have these magnetos that you've probably gone over, right?
Yeah, he knows all about
the magnetos keep the engine going, but they will not. The alternator is strong enough to keep the battery and the airplane systems going, but it's not strong enough to keep the engine running. So the alternator is going to I'm going to get down the current thing. So the alternator is only strong enough to provide enough electricity for your battery to provide the aircraft systems to operate. When you have what's called a do this. God, I'm trying to keep it simple for you.
You're good. You're doing a great job. Seriously.
Yeah. How do I want to do this? Man, I'm going down a rabbit hole. I know.
The alternator keeps the battery charged.
Yeah, and then the battery keeps the airplane systems going, but they all three work in tandem. They're all three working together.
Tell you what, why don't I'll pull up an electrical schematic in a little bit, but for now, why don't we talk a little bit about voltage and amps and kind of what those are?
Where'd the thing go with the bottom?
Let's hit
that. Okay, there. All right. I was trying to segue into the volts and amps thing, but I'm just the way I started going over it, and I'm realizing that I don't like how that worked. I'm just sorry. You're one of my guinea pigs here because everybody has different.
No. That's okay.
I'm trying to figure out a good way to teach you all how to do this. And all right. So let's just go a simple diagram here. Hopefully it's simple. So you have what's called a river, of course, which is water.
Mm-hmm.
Okay, this is my river, and the width of the river, we're actually going to call the voltage. Okay, so depending on how wide the river is consider the voltage. I could have a skinny stream and it has a small voltage, or I could have a wide river. It's a large voltage, right? So if the river is not moving, if it's just sitting there, just stagnant, right? It has the potential to move a lot of water, but it's not.
Okay.
Then you have what's called the current. All right. So the current comes along and starts pushing the water. So that is what we consider the amperage. So let's just say that's the water, starting to push. So this becomes the current. This is the amperage. Okay. So you could be standing in a very wide river. Okay. Mm-hmm. But it's very shallow up to your ankles. Do you think that has enough current to knock you over?
No.
Right. So if I were to take this same amount of water and put it in a very small stream, right?
Mm-hmm.
So your voltage here is now very small, but think about all this water going through this little river, right? That's a lot more water, right? So you've got 1,000 gallons pushing on you here in this giant river. If I have 1,000 gallons trying to push through a little stream, right, and you're ankle deep, think about how much more pressure is going to be coming at you. So that's why people don't realize that you have small voltage here, right? The stream is the size of, or the voltage is the size of the stream is small, but you have a lot of current. That that ankle deep water with 1,000 gallons is going to knock you over quick, right? That's why current is dangerous. Current is the amperage that kills you. All right.
Okay.
Voltage has nothing to do with. I want to say nothing, but it does not have a large effect on.
Right. It's not the direct effect.
Yeah, it's not direct. It's indirect. You can have. I've been zapped with thousands of volts. I mean, it happens. You have when you touch your finger to metal. I mean, people don't realize. They see 50,000 volts. It's like, so what? It could be 50,000 volts, but it could be such a minute current it won't hurt you.
Right.
And that's also how people survive lightning strikes, because they are, the voltage is huge. It's like what, million volts, right? But the current inside lightning is so small. Well, not so small, but it's small enough where it has the ability not to kill you.
Gotcha.
So when you see these signs and stuff that say like high voltage, keep out, is that just because popular culture has taught people that voltage is what kills you?
Pretty much.
Looks more dangerous than high amperage or whatever.
It is. And
it's more severe looking word.
In reality, it's high amperage. Let's go that route. But people don't recognize what goes on, within electricity and how people see the word volt and they get scared, right? When you hear amp, you're like, oh, it's okay, amp, whatever. But yes, amperage is what's dangerous. Voltage is not dangerous.
Okay.
Voltage is the potential for you to get hurt. It's not what hurts you. Let's go that route.
Okay.
That's kind of I always see those high volt. I'm like, who cares? It's like, because the word amp does not scare people.
Okay.
So the word voltage scares people. It's just a potential for you to get killed, not what kills you.
Okay.
So let's say on an airplane, you have or in the river. Sorry, in the river, you have little rocks. All right. Those little rocks create resistance, right?
Sure.
So that is where you get your R from, your resistance. And those little rocks, say if this is an airplane, you got your voltage from your battery, in your system, your battery, you got amperage from your battery, you got these little rocks, which are resistance, which can be light bulbs, they can be motors, they can be, they are whatever you want to run, to do some sort of work. So you have to, that's
it's what's drawing the energy from the river.
Yep. And resistance will create either heat, light, or something, which is what you want a light bulb to do or a motor to do. So that's the kind of my little river analogy is,
Yeah, that's
current is amperage. River, it doesn't matter how big or how small. So this river, we could call this river 28 volts the 28 volts wide. We can call this 5 volts wide. Just about the size. I don't like how it's not doing that.
Okay.
Yeah. So again, voltage is not what kills you. It's what lets gives the path for the current to kill you is pretty much what it is.
Okay.
It's a real question.
Okay.
So let's say we have the river on the left, okay, with the high,
very wide,
shallow river.
Okay.
If those little rocks were light bulbs,
yes,
would the size of the river have an effect on the brightness of the light bulb versus if those rocks were in the skinny river?
No,
Okay.
because the way the circuitry is designed, the light bulb will stay. Well, let me say it. The light bulb will stay bright. What it's designed to stay at, because the light.
So it's wattage or whatever.
You can change the 28 volts can be constant. So the river is as wide as it's going to be. It's constantly the same size, right?
Mm-hmm.
The light bulb resistance 28, 10 watt, 15 watt, that is constant. So the size of the river is constant. The light bulb is constant. The only thing that changes is the amperage.
Okay.
That is what we adjust, or what gets adjusted to make light bulbs brighter, dimmer.
Okay.
Yeah.
Okay.
So, and that's where it comes in this Ohm's law, where it's, if you have two fixed variables or two fixed parameters, the other one's variable, which is amperage. So this could be a dimmer switch. I can turn the amperage up.
That's exactly what I was going to ask. Yeah.
Yeah. So the amperage is.
So we can increase and decrease the speed of the river, is what you're
correct.
saying.
Yes, by adjusting the amperage, you're increasing and decreasing the speed of the electrons that are going in and out of or going into the whatever you're doing. So yes, like a dimmer switch, I could turn up from 1,000 gallons to 2,000 gallons, and that but the way the system is designed is it's the way if it's fixed, there's got to be something that changes when you change one or the other, right?
Mm-hmm.
So I'm going to do this real quick. So V equals IR. So voltage equals current. I is the abbreviation for current, and yeah, it is. Yeah. So V equals IR. That is the simple electronic formula for everything in the world. So if my voltage stays the same and I adjust my current, my resistance is going to change, because that's how, to keep
it's algebra.
Yeah, simple. If the light bulb is, if
you could have 8 equals 2 times 4 or 8 equals 4 times 2.
Yeah. So it's very simple. So if you have one constant, which would be the 28 volts. I'm horrible at drawing. 28. So say we have the 28 volt, and then we have this R is a light bulb. Let's say this light bulb is 10. I'm gonna just call it 10 ohms. I mean, that's because resistance is used in ohms. That's how we do it. So if I adjust the current, so we have two fixed. By adjusting the current up or down, that's going to stay same. The resistance of the light bulb is actually going to change. It'll get brighter to a point where it stops.
Okay.
Because of the way it's designed. I know it's going to get way into. If you exceed the design limitation, the light bulb will explode. It's pretty much you got it. That's where it comes in, this fine line of what circuitry design, which engineers do. They figure out how many, they figure, okay, this light bulb is 50 or this light bulb is 10 ohms, the voltage is 28. We got to make sure our resistance doesn't exceed, so if we do this, 10, so we got to make sure it doesn't exceed 2.8 amps, because 10 ohms, 20 volts. So that's where they do their calculation to figure out, how much can the circuit handle.
Okay.
And I won't get super into it, but they'll actually put other pieces of resistance in the circuit to prevent light bulbs from exploding. So
okay. That makes sense.
Yeah. But again, all you gotta know is voltage doesn't kill, current kills.
Should get that on a t-shirt.
Yeah. So the amperage is what's doing the work pretty much. The voltage just enables it to do the work.
Okay.
So and then I'll get down in the wire on the airplane. So you have a wire. You can consider the wire as the voltage. Okay. The size of the wire determines how much current can go through.
Can go through, yeah.
Yeah, how many amps can go through that wire. So you'll see, like when you look at the battery, you'll see those giant wires, right? There's that is a lot of current going through that, but it's 28 volts, right?
Right.
Okay, so you see, if you look under the instrument panel, you see those little wires. It's a little current, but it's still 28 volts. But it's the stream. So I would say, what I would say is, this is your battery terminal. So consider this giant river as your battery terminal. Consider this small river as your wires underneath your instrument panel. They have the exact same voltage, 28 volts, or is it 12 or 28 on you guys? Are you 12? Is that what the battery is on the Cessna? Is it 12 volts?
It's 14 volts.
14, right? Yeah. So yeah, big airplanes are off 28 volts. So I'm stuck in big airplane mode. But still, just so you know, doesn't matter the wire size. It's still 28 volts, whether coming off the battery or underneath the instrument panel, or 12 volts or 14 volts. The current, the size of the wire determines how much current is. In that circuitry, and some engineer figured out that it is safe to operate that circuit with that wire size without causing, any problems.
Okay.
I do have a question as well. So what determines the size of the battery required for the airplane? For example, pretty much every 172 I've flown has been a 24 volt battery. Things like the Archer and the Duchess are 12 volt batteries and 14 volt systems. So why?
It probably just depends on who calculated, the engineering figured out, okay, we can run it off of, so I guess back in the day, the bigger the batteries you had more power consumption. So I can't speak for the little airplanes. So the big airplanes used to operate off of 48 volts. World War II back then, you had those big batteries. As technology advanced, you were able to shrink the battery, so you weren't required to have as much voltage, or bigger voltage, whatever. It may be the same thing with little airplanes, where as technology advanced, you don't need that much capacity in a battery to do, all the to operate it. Or it just might be it's kind of like, in the United States, we operate off 115 volts. Over in, other parts of the country, you operate off 220 volts. It does the exact same thing. It just may be what they like to do. It just might be a choice. It would have no bearing on design. It's just that it's a preference. But everything started, everything was high voltage back in the day. Back in World War II, they had multiple batteries, and they're heavy and big. And as technology got better, they didn't need them, so they were able to didn't require as much. The wires got thinner and smaller. The battery got smaller. The electronics got smaller. So maybe they just didn't say, why, it's overkill. Why do I need this much? When it'll go to an optimum circuit is designed to be 5% below the failure point. If you think about that, so if you increase the demand on your airplane electronic circuit by 5%, it'll fail. That's a very small threshold. Do you understand?
Kind of.
So that's the way circuitry is designed, on the threshold of failing. Okay. That's the way the safety, the fudge factor for this airplane catching fire because the wiring is like 5%. That is, but it goes into weight savings as well, as they design stuff on the threshold of failure just to make it to be safe, So yeah, that's pretty much my spiel about, voltage is the size of the river, or the size, and the current is the amount of water going through that river, and the resistance is the low light bulbs.
So with regards to the aircraft, you have your circuit breaker panel, right, Cooper?
Yes.
And all the little circuits have little numbers on them, right?
Yeah, like 1 through 20 or whatever, right?
Yeah, they've all got little numbers on them. What do those numbers represent?
I guess the wire that they're representing, maybe.
No.
You have ones, you have fives.
Yep, there's a 20 in there.
20. The little number on the circuit breaker.
The amount of current that can go through it.
That's correct. That is the rating, how much current can go through it before it will pop.
It pops.
Yes.
So all of those little items are rocks in the river. Most of them.
They are connected to rocks in the river. Yes.
They're connected to rocks in the river.
So that's so you have to that circuit for that circuit breaker. So let's draw it. So I'm going to draw your battery here. I know it's a horrible thing. I'm sorry. I'm horrible at this.
I can pull up the electrical schematic for the airplane if you want to.
So then you have this thing called. This is how we draw a circuit breaker in the electronic world. And you have your light bulb. If I draw a light bulb, good. Okay. So and then this goes back to ground. So this is the ground. This is a ground signal. This is how we draw a ground, and this negative here. Actually, let me do this. I'm going to draw it backwards here. So it's not so complicated. So here's your wire coming out of your battery. So it is understood that these 2 points here and here are connected because they are the same. They're the same drawing. They look the same. That is your ground. Okay. This is your airframe, the metal part of the airplane. So that's how we finish the circuit. We complete it by going through the airframe from wherever it's at back to the battery. So that's all you need to know for that. So when I draw that like that, or if you ever see it, this little ground signal like that, just understand that this point and this point are the exact same electrically, not physically, but electrically. So let me draw a little switch here. I wish I had a eraser on. I keep grabbing this iPad.
I'm just going to take this off, and you can just see it's a plug.
Okay. the back of this pen, I keep turning over trying to make a erase on the screen. So here's our simple circuit. Here's our light bulb. This is a circuit breaker here. So let's say you have your I'm going to say 14 volts. 14 volts. This light bulb operates off 10 ohms. So say if real quick, so the current of this circuit is going to be I equals E. Actually, I'm gonna call it V because there's another thing. Electricity is voltage is not V for engineers. It's E. Yeah, it's so
of course.
Yeah, it's called electromotive.
So we've taken the formula and just rearranged it.
Yeah, so I've taken that E equals I over R, or the V equals I over R, and I've actually just changed it around to wrote it a different way, but it's the exact same thing. So current is voltage, so 14. So let's see, I equals E over 10. So what is 14 divided by 10?
I got my
1.4.
calculator.
1 point. So
I don't even know.
1.4.
Okay.
Yeah.
1.4. That's 1.4 amps, right?
Mhm.
So this wire with this light bulb will carry 1.4 amps. Okay.
Okay.
That is how an engineer designs a circuit. So I know the voltage, I know the battery, I know the resistance of the light bulb, I know that's how much current is going to be running through this circuit. So if I have a circuit breaker in that circuit, I need to say, okay, if I have a 1 amp circuit breaker in here, right, and I turn this light switch on, and 1.4 amps goes through here, that circuit breaker is going to pop because it's not enough.
Okay.
So that's where the engineer says, okay, what if I put a 2 amp circuit breaker in there? So they put 2 amp. So now you have a 2 amp circuit breaker, and you have 1.4 going through this. That circuit breaker is not going to pop.
6 left over. Yeah.
You got it. Yeah, right. Now the engineer's going to say, well, how can I save weight? Engineers.
So does anything happen to the light bulb because you're sending too many amps to it?
No. The circuit breaker will pop before it gets to that light bulb.
Okay.
The circuit breaker protects the circuit from catching fire is pretty much its only purpose in life.
Okay, so we're sending enough amps to the light bulb, but we're not sending too many to pop the breaker.
Correct.
Okay,
so
gotcha.
yeah, as long as you have a 2 amp and you have a 1.4 going through, the circuit breaker limit has not been exceeded.
Gotcha.
So engineers are going to say, hey, you know what I could do? I'm going to put a 1.5 circuit breaker amp and 1.5 amp circuit breaker in there. So we're going to be right on that threshold of failing because it's going to save me. It's going to save me like 6 ounces of weight. It's
sure.
Right. So that's how a circuit breaker, and you'll see those numbers. That number on that circuit breaker is the maximum amount of current that circuit can handle before essentially the wiring catches fire.
Okay.
All right. So, and if you actually go and add up all those circuit breakers, it should not exceed the battery current limit, which is 60 amps.
60 amps. Yeah.
Yes.
Okay.
And so if it does, you're gonna get a fire on board because something's gonna overheat. So
okay.
Circuit breakers actually is kind of funny. Circuit breakers were designed to protect wires, not electrical components. That's the whole purpose of a circuit breaker is to protect wiring. They don't care about the components. They don't care about light bulbs. They don't care about motors. All they care about is the wiring. Because when the wiring catches fire, it's bad because it usually catches everything else on fire.
Yeah.
So when a component gets too much current, it just burns up internally inside the box or whatever. And it's protected. But so there you go. So that's your quick little rundown of a circuit breaker. Is circuit breakers, that little number on the circuit breaker is the amount of current the circuit can handle before the wires catch fire.
Okay.
And that's how it's designed. Just you know what the voltage is. You know what the resistance of the light bulb is.
Mm-hmm.
You know how much, what kind of circuit breaker to put in that airplane.
Okay. Gotcha.
Okay. Yeah. All right. So, see, I want to go into next.
Alternators and generators.
Yeah, alternators. Oh, God. Do you have the? You know what? Can you pull up the? I don't want to get too far into generators because you guys don't really.
You want me to pull up the POH? Is that what you want?
Yeah, give me something with a schematic. Yeah.
Okay.
So, yeah. Now we're gonna start getting into magnets.
Oh boy. Okay.
Yes. Because we've been talking about batteries right now. So pretty much the battery just has the electrons inside it.
Okay, we've got a whole bunch of stuff in here on the electrical system. Starting with the information about the electrical system, and then we've got
let me
this, and then we have this.
Yeah, let me look at this. Can I draw on this?
You can right there. Let me change the thing. There you go. That should work.
All right.
And you can't erase, but you'll just have to like clear
Every time.
if you can.
All right. Can you see the screen?
Yes.
All right. Let me look at this.
Stop doing that.
I got it.
Here, you can turn this right.
How do I change pages?
Oh, you gotta turn the pen off.
Okay,
and
so
then
that's
turn
like
the page.
all right. Let me see what I got here. See which one's gonna be better for me here.
Do you want to bring up the actually we can bring up the we have an interactive electrical schematic
Yeah.
where you can actually move and turn things on and off.
Okay.
Here, yeah, let me do that. That's on our website. No, I'm good.
All right.
Under the customer resources tab. You can't draw on this, but you can click things on and off. Okay. So on here, you can like tap things and it'll tell you about things.
Mm-hmm.
And hang on.
Do we tap on it again?
No.
Yeah.
Okay.
So does it?
So you've got all of our circuit breakers up. It's loading still. That's what's going on with it. You see the blue bar up there. It's just still loading.
That's what you get from stealing from University of North Dakota.
It's a website. So you've got your little, but you can see your little ground things over there, like with the battery.
See on the far lower left, you see the little on the battery. You see that little with the
ground symbol.
That's the ground symbol. Yep, that is
one on the standby battery.
Yep, you see them. They're all over the schematic. They're on the battery master.
Oh yeah.
So you have to think of it as
the starter.
Everything, all that stuff, all those little connections are connected to one common point, which is the airframe.
Okay.
And the battery master and the alternator master are the same switch.
Yep. That was okay. Yep.
Because they're the same size.
Yeah.
Right?
Well, same. What do you mean?
Well, they're the same. Like they look the same.
Yeah. Those are same points electrically. All the if you see that little ground symbol, they're all connected everywhere on the airplane.
Something's wrong with the Wi-Fi. Yeah, everything's fine.
Yeah, let's say it's.
I don't know. It's just like it's not loading.
Reload. Try reloading the web page again.
Well, it is. It's getting there. Our breakers are starting to load. Yeah, it's just super slow.
All right, I'll work off it. Let me just.
Yeah, we got this little spinny thing up here at the top.
All right. Yeah, whatever.
So you can bring up your switches.
Okay.
As well. And you can bring up your master switch, and all you got to do to turn it on is just click it.
Okay.
Okay. So and you can turn the engine on and off too.
Okay. Does it do anything when I turn the engine on?
Yeah, it is. Like if your master switch is on.
Okay, so I got to do the whole thing.
You can see everything's orange because it's being powered by the battery. But when you turn the engine on, it becomes powered by the alternator.
I got you.
Yeah. So then we can. I don't know what's. Yeah.
Okay. Well, I'll play with it here. All right. So initially we have our battery down here on the bottom. I guess can't draw on this, can I know? Okay. The bottom left corner. So then you have your power distribution module. So I'm not assessing the person, so I'm gonna have to figure this out. But I assume it's probably
that's the box.
I'm about to say
it's the box that's behind the cowling.
Yeah, I'm gonna say it's in its own container,
mounted to the firewall.
Yeah. So inside there you have a bunch of circuitry, but everything is connected to. You have the starter and the alternator. Okay, so we've talked about the battery. It just sits there and has the potential. It has the negative, positive electrons just sitting there waiting to do something.
Right.
So now I'm going to explain how do we create electricity, I guess you want to say, or how do we recharge the battery? How do we generate something from pretty much nothing. And that's what we do, what we call the alternator.
Okay.
The alternator is a component that has magnets and wires in it. And when you spin a magnet or a wire or a coil of wires, you take wire and we wrap them in a certain pattern.
Yeah.
Where's an opening?
Twice.
Okay. So yeah, we have a magnet and we have coils. Let me see if I do this here. So let's say this is our magnet, and then what we have is we have a bunch of coils of copper wire. Okay.
Okay.
If I take this magnet and I spin it clockwise, counterclockwise, it doesn't matter. If I spin it, what you have is that magnetic field is cutting through these copper wires. It's actually, the magnetic field is affecting these copper wires. And yeah, well, I didn't draw that on there, but yeah. So, the magnet has a north and a south, and the magnetic field coming off of that magnet is essentially electrically cutting through these copper wires, right? What we do is we take that, when that magnetic field cuts through the copper wires, it actually creates a current. It charges up the electrons that are inside that wire, inside the copper wire. We actually tap off of that and we send it to the airplane. It's invisible. You can't see it, but it's happening. It's
creating an electrical field. That's why that circuit breaker is called the alt field circuit breaker. The one in the on the panel on the upper left-hand corner, the one that we check if we have a low voltage annunciator that comes on. The alt field circuit breaker. What is an alt field? It's literally the electrical field being created by the alternator.
Yep.
Okay.
So that circuit breaker in theory is, so you have your magnet spinning inside this coil of wire. You'll see it's round. The alternator is round. Inside, you're going to have the magnet right in the middle, spinning as fast as it can on with the airplane engine, and that magnetic field is cutting through these copper wires, and then we take that. Cats are going crazy over here. So we take that that magnetic field, and it actually starts moving the electrons. Well, we take those electrons and we tap off of this copper wire and we send it to the airplane, to the whatever that module is called, right?
Yeah.
The power module, whatever. Power distribution module. But here's your field circuit breaker right here. If I could draw an F, I had something to drop here. But yeah, that's your field circuit breaker right there. So we don't have one wire. We have probably around, I don't know how many more they put in there. Probably close to 200 or 300 wires inside that alternator. So we have multiple coils creating the electrons. It gets the electrons moving. So actually, there's a ton of wires that connect together from these different coils that creates one big wire that comes out to the airplane, which goes to your field current circuit breaker. So all you gotta know is magnet spins, creates a magnetic field, or magnetic field cuts through the wires, and it starts generating current. So instead of a battery, we have a spinning mass, right? Does the exact same thing.
Right.
So that's as far as I'll get in with you with that. But alternators and generators, you've heard generators, of course. Alternators and generators do the exact same thing. The only difference is the physical design. Whereas on some generators, you have a magnet that spins.
Mm-hmm.
And then on some you have they actually spin the coils of wire, and the magnet is stationary. Does the exact same thing. It's just how the design is. The thing about alternators is they're very small, they're compact, and they're light. And that's why they're used on small airplanes. where big airplanes have generators. They're heavy. They're probably close to 70, 80 pounds on the big engines.
Okay.
But they are used more for the bigger the alternator, the bigger the generator, the more current is created, the more windings you get in there, the more coils, the more copper wire. You don't need to put a giant generator on a small airplane, so that's why they have that. You can hold this thing in your hand. Do you have one in the office?
We do. You've seen those alternators. I have a couple of them on my shelf.
So
yes.
You're gonna look in there, and you're gonna be able to see. You should be able to see the coils of copper wire spun in that pattern. And when you spin can you spin the shaft on it?
Yeah.
Yeah, you're spinning the magnet.
Yeah, it's it's that little gold piece with the fan looking blades on it that we can spin.
Yeah, you're spinning. You're spinning the magnet in there. So essentially, that's all I need to know is you got a magnet spinning with copper wires, and it's creating a current. That is it. All right. So inside this alternator over on the left, that's pretty much it. It's spinning. The field, that is your the current coming out of it, and then the alternate input. I have no idea what that is. That's a Cessna thing.
Say again?
What's the alternate input? I don't know what it is.
Where do you see that? Oh, alternator.
Yeah. What is it?
I guess that's where the alternator is connected to the alternator control unit.
Yeah, I guess it's probably electronic something or other.
Yeah, that's like where your here, if you click it right here, you can see, and it'll tell you what the alternator control unit is. So that's basically, it keeps your voltage regulated.
So this one is 28.5 volts instead of 14. Okay. Yeah, it doesn't explain what that input thing is, but
I think that's just how it's connected.
yeah, I don't know. Anyway, so big wires come out of the alternator. Magnet spinning cuts the coils of the copper, creates an electric current, sends it into this power distribution module, and then you follow these wires through, and it'll actually send it to. That's the ground sends power in, all that. So it sends it to the alternator output, which goes through the alternator relay.
Why don't we talk about what a relay is?
Okay. Yeah, I guess we get into that basic relay stuff. All right. So you've heard the term relay, right? Of course.
Relay races. Like in the Olympics.
Yes.
Do you know anything about a relay? What it does?
Nothing.
Okay. So you see those big wires coming off your batteries. So when you send the when you turn the key on the magneto or turn the key in your car, do you want all that current from that battery coming to that key and going into the starter? So let me draw this battery here again. So let's go. I know it's going to be a horrible picture, but so this is that's going to be my key. It's a horrible thing. And then we'll put this as a starter. So bat comes up here. Such a bad draw on these things. So, all right. So here's your starter for the airplane. So you have this current. You got this giant wire, a lot of current. What is the current to start on the starter? Do you know? Is it in here?
Yes.
We'll show it in here.
Yeah, we can.
No.
Is it going to be? I don't think it's going to be on the breakers.
Oh, it's there.
I don't know if the starter is actually on there.
Bus transponder. Flap. No, I don't see it.
Don't know. Over here, if we click on the starter, no, it doesn't say.
Anyway, just so you know, to start the airplane, that's a lot of current, right?
Okay.
You need a lot. You need a lot of because that engine's big and you need current. So you have a lot of current. Do you want all that current coming down into the cockpit into that key when you try to start it? I'll say that if something internally shorts out inside that key, it's going to hurt you.
Okay.
Right? Amperage. You don't want that amperage in there.
Think of those cartoons where like they get electrocuted and then it's just like buttons.
Yeah, that's pretty much it. So for safety, we created things called relays and solenoids. And the purpose of a relay and solenoid is to control a large amount of current with a small amount of current.
Okay.
So what we have done, actually I probably shouldn't have done that, but so we have taken something and we've created what's called a start relay. So the start relay, but we have actually broken the circuit out and we have actually like I'm doing that. So we have a thing here with a relay with a coil in it. Okay. And this coil creates a magnetic field. You run electricity through a coil, creates a magnetic field. Or you spin a magnet that creates electric field. So there's coils create electric fields. That is a known issue or a known thing about electricity. All right. So instead of running the wiring from the battery to the starter, we put it through this start relay, and we have a switch, or we put the switch here for the key. So in theory, and I'm not going to draw the whole circuitry, but when I turn the key here, it's going to create a current in this circuit. Remember, it's a complete circuit. Current flows. That relay is going to create a magnetic field, and it's going to actually pull this contactor down and create that circuit. And it's going to send the current from the battery to the starter through this relay instead of through that switch in the cockpit. It's for safety. It's for safety. You control a lot of current from the battery with a small amount of current, which this could be, like milliamps or tiny bit of current. Where this is up here around, it could be almost 50 or 60 amps. So this will kill you up here. This isn't going to do nothing to you down here. It's such a small amount. So that is the whole purpose of a relay. It is it controls a lot of current with a little current. So here you have your start relay. Right. So you see the little you see the start relay inside the module?
Yes.
So you see that where it says start relay, you have the little bubble.
Oh, I was just trying to.
Oh, start it.
Right.
Let me see here. All right. So the start relay. So
you can see the battery relay just closed there.
Yeah,
with the battery on.
Yeah, the battery. So again, the battery's got a lot of current too. Remember the big wires. So there's a battery relay too, because you don't want your avionics master. You don't want giant wires coming to your avionics master switch because it'll hurt if something shorts out. So the relay here it is connected. If you follow the wire all the way across through that, just below that feeder A to your ignition switch. That is the small amount of current in that wire, and then the large amount of current is coming out of that starter, and that little relay will close. And let me see if I get to start here.
I don't.
Let me see. Engine start. Is there engine start?
No, it just goes on to off. So I don't think that one actually.
There's no so you can't see that start relay.
Yeah.
But yeah, just so you know that the relay
when you're cranking the starter.
Yeah. When you turn that key, that starter relay closes or comes down. That line comes down and sends current to the starter to start the engine.
Okay.
Okay, so large amount of current controlled by a small amount of current for your safety. So it's a remote switch somewhere else if you want to kind of think of it that way. So the alternator is sending its so say we get the engine started, starter's done, engine's running. So the alternator is now generating current, and it comes through. Yeah, that's starting. Okay, engine's running. So you see alternator output comes out of your alternator control unit, goes through your alternator relay, and it starts powering all your circuits in your aircraft. But it's also at the same time, it's actually charging your battery, because you see your battery is red now, so it's actually going in and fantastic.
No, it's just showing.
Oh,
the red is.
Yeah. So the alternator is now charging the battery and running the circuitry of the aircraft.
Okay.
So can I open circuit breakers?
Yes, you can. You can just tap on it. If we pop the alternator field circuit breaker.
Mm-hmm.
Okay.
Okay. So you lost your.
That's this one right here in the middle. You'll see it just above the word circuit breaker on this little thingy here. Can you see where it says alternator field circuit breaker?
Yeah.
Okay.
Yeah.
Yeah. So you can see the breaker, and then we can pop it back in. Whoops.
Yeah, let me tap it. So normal running, your alternator is powering everything. If I open that circuit breaker, now your battery is powering everything.
Okay, I got you. Yeah.
So that is your that's pretty much your output to your to run the systems on the airplane. Let me see, is it working?
Gotcha.
Okay, so also you're going to see over here inside your power module, you're going to see your alternator relay. You're going to see that move. That's going to move up and open and close as it comes out. Yeah. I'm going to cut the warning here. I didn't mean to hit the warning thing. I don't know what that does, but anyway, that's kind of neat. So alternator powering the airplane. Alternator is a spinning magnet with coils, and that's generating your current here for your running your systems. I will go over this real quick. So an alternator, I'm going to take you back to high school. All right. See if you remember, you remember in math, a sine wave?
Wait, what was that?
Do you remember what a sine wave was in math?
No.
All right. So, what's called a sine.
Common core.
Yeah. Okay. It's common core. Okay. So we have here, which we're going to call this 0 volts. Okay. Which is a line here. This is 0 volts. We have here we'll call this 14 volts here, positive, and negative 14 volts here. Okay. So we have a sine wave, and SINE. Well, sine. Yep.
Oh, yeah, I know.
Like sine, cosine.
Sine, cosine. Yeah. So.
Okay.
So here is your sine wave. So you have the sine wave coming out. So this is what the current coming out of your alternator looks like, because you're spinning. You're going. It's cutting through those lines of magnetic or lines of coils. So you got a negative, positive, negative. Remember, your magnet is north, south, north, south.
Mm-hmm.
Right. So your actual sine wave looks like this. So it's north. This would be north, be south, north. Going down here, south. So this is what it looks like coming out electricity wise. If you looked on a special meter, this is. And the thing about the airplane is it doesn't like this. It doesn't operate, because if you ran the airplane on electricity like this, it would just be a strobe light. Everything would be a strobe. It would be on, off, on, off, on, off. You look like you're in the club, pretty much.
Yeah. All right. That's what I was thinking.
Yeah. Blinking on and off, on and off, on and off. Yeah. We don't want that. So you have inside the alternator things called rectifiers. And what they do is they take this sine wave, and they actually stabilize it to a constant 14 volts. So for purposes, I'm just gonna do this. I'm gonna say, okay, so we have your sine wave goes inside this rectifier, and after it goes through all the circuitry, it comes out and it just stays a constant 14 volts. Those rectifiers you can see on the alternator. They look like little pucks, little
gold piece of that.
Yeah, they're little, and pretty much all they do is electrically they take that sine wave, and they actually just make it a stable 14 volts positive.
Because an alternator produces what kind of current, Cooper?
DC.
An alternator AC. Produces an alternating current. What does our airplane run on?
DC.
So how does that work? Circlet.
I don't know.
Rectifier. The rectifier converts your AC to DC.
Okay.
That is how everything operates. Stabilizes it. Everything runs great. So, but there are inside that alternator, there are 3 of these. Should be 3 of them, I think. Yeah. On yours, yeah. There are 3 of these rectifiers, one for each section of alternator. There's there's one magnet, but there's three sets of coils. So each one of them has its own separate rectifier. So you get 3 rectifiers that come out with one 14 volt DC output. So I keep wanting to say 28 volts. So that's where you have. It doesn't show it in here, does it? No, it doesn't. But all you gotta know is inside the alternator.
Just a heads up, I have to leave in about 5 to 10 minutes for an appointment.
All right. We'll keep. This is. All right. We'll just keep going, and you let us know when you need to leave. Is there anything specific else that you wanted to kind of understand about?
No, I mean, I think this covered way more than I expected, which is great, and it's been perfect. Like
you do not have to
example
teach
was perfect.
How electricity works, but you've got to it's just to kind of give you an understanding, so you know what you're talking about when you talk about volts.
Yeah. Okay. Yeah, that totally makes sense. Yeah.
But just keep going, babe, and we'll go until he's got to go.
So I'm going to try to do a couple things here real quick. Okay, so you have the where's the meter? Where's that print with it? Like that way in the front here. Say some stuff you can notice next time your phone. Okay, here we go. All right. The say 20. They call it 20 volt here.
Yes, 28.
Okay. So you're gonna notice here you have your ammeter here, right?
You can also turn this up.
Okay, you have your ammeter, right? So your battery has a rating on it, an amp rating. Whatever that may be. I don't know what your amp ratings are on your batteries. It probably doesn't say it.
No, it doesn't.
So when you look at this ammeter, do you know what it means when the needle's moving?
That there's current going through.
Yeah.
Positive charge.
Yeah. So you have your positive, your negative. So that pretty much tells you charge, discharge. All right, you don't have needles, so you really can't do it. All right, so it's just so that may not be a good example then.
All right. But it just has a number, and it'll show a higher number or a lower number.
Mm-hmm. Okay, yeah, but pretty much you can tell. I don't know, if it's a positive or negative charge. Positive. I don't know how you guys do charging, discharging. If it's positive, is it charging?
Yes, if it's positive, it's charging. Think about when right after you start the engine, Cooper, and you look at your look at your EIS, and you see a high amps on your main battery, because the alternator is charging the main battery because the main battery was really drained during the starting process.
Right.
So usually, if everything's charged, you're going to see 0 amps because it's not charging it anymore because the battery is fully charged.
Okay. Oh, okay.
But if the battery was being drained and being used, for example, like during the starting process, then it's going to show a positive charge on the battery because the alternator is sending more power to it because the battery was drained in the starting process. Does that make sense?
Right. Yes.
So in a way, when we teach in the big airplanes is to check the health of your battery charging circuit. Your current should never exceed the number that is on the battery. So like we have 36 amp batteries on our big airplanes. If we ever see the current go above 36, something is wrong. That's just okay. So you should never see that current go above what the battery is rated for because it's overcharging and it could.
We do have an over voltage checklist. If we look on here,
yeah,
high volts annunciator. So if the main battery bus volts is more than 32 or the main battery amps is more than 40,
there you go.
So what would cause that to illuminate?
Are you asking me?
Yeah.
So what would cause a hot, like a excessively high annunciation? I don't know, induce stress on more, I don't know, an excessive flow of something.
So over here somewhere, we've got our over voltage.
The low voltage.
Yeah. We have our voltage regulator, which is somewhere in here.
It's got to be internal in there.
Yeah, it's gonna. Yeah.
It's on the old print probably.
Yeah, it's gonna be probably in the POH. Oops. I think it's in the.
Is it internal there?
Yeah, I think so. Because you've got a a voltage. Talk about what a voltage regulator does.
Yeah, pretty much voltage regulator does what it does. It maintains a constant voltage, and it will adjust the current inside this control unit to maintain a constant voltage. Remember the whole, if you know your voltage, your battery, you know what you need. You can, you can use that Ohm's law to adjust. This thing automatically adjusts for it. But if you do have a failure of your voltage regulator, it's going to, you're going to start having a lot of issues. If you have high voltage, you could have high current because if you change one, you change another parameter. If resistance stays the same, high voltage will cause a high current, or a high current will cause a high voltage, just depending on what you have going on. But yes, voltage regulator is pretty much what it does. It's supposed to maintain that 14 or 28 volts or whatever, 24 volts, whatever you have. It's all internal to that box, which I don't know what does. So I don't know. So yeah. When you see a high voltage or a high current, your voltage regulator is starting to go out.
Look at what we've got to do to protect the aircraft. Is basically turn everything off.
Yeah.
If you left it on, circuit breakers would start popping.
Okay.
Pretty much where you'd be at it. So this is, you don't want circuit breakers to pop. But again, if you didn't do any of this, the circuit breakers would eventually start popping until the point where either the voltage or current got down to where it would maintain what hasn't popped, or or something burns out completely. So
gotcha. All right.
Yeah, I don't know what's going on inside that module, so it's hard to see exactly what's to it.
Yeah, there's in that book that Rick has, it's got a picture of the power distribution module, and basically it's a bunch of little tiny little components. You can see your everything. Oh, is that your alarm to get going?
Yeah. Yeah. Sorry.
All right. Do you have any additional questions? I'll just a couple things I want to point out about this this diagram right here. We haven't really talked about the standby battery too much, but the standby battery we know how of course powers the essential bus, right? Which is this one right here, which is a very limited, number of items in the event of an absolute dire emergency. One radio, your PFD, one nav, the standby indicator lights, and that's about it. And we can talk a little bit more about this in person. And I can explain a couple more things on how some of these things are connected with these little like one-way diodes and stuff. We can talk a little bit more about that in person, but I just wanted to make sure that you kind of got a basic.
Yeah, no, this was great. Thank you very, very much for doing this. I really appreciate it.
Yep. So remember, current kills, not voltage.
Yes, I have that highlighted.